Class, welcome to the next lecture. We're looking at sum and different identities for sine and tangent, and we'll be using the sum and difference for cosine to kind of build these identities. So we're going to look at sum and difference for sine, sum and difference for tangent, how to apply these sum and difference, and then of course we're going to do another identity verification. We can use the cosine sum and difference identities to derive similar identities for both sine and tangent. For example, if we're trying to figure out the sine of a sum of two angles, we can recognize that sine and cosine are cofunctions, meaning that the sine of an angle is equal to the cosine of its complementary angle. So we can rewrite the sine of a plus b as the cosine of 90 minus a plus b, and then use the cosine difference identity here by going ahead and distributing this. So of course, if we apply the cosine difference identity, we get cosine, cosine, sine, sine. Cosine of the first angle, cosine of the second, plus the sine of the first angle, sine of the second. Well, we notice that 90 minus a is actually going to change the value of that, or the trig function, because now, since we're looking at the cosine of 90 minus a, and this is the cofunction with sine, because they're complementary, we can just swap those both out, and we get the first identity, sine a cosine b plus cosine a sine b. So we notice here that unlike cosine, where the functions are the same, cosine, cosine plus sine, sine, sine of a plus b is actually sine of the first angle, cosine of the second, plus, and then flip the functions, cosine of the first and sine of the second. Okay. We can also now do the similar thing, or actually use a negative angle to use the sine identity we just created and create the difference identity. And so we can see here that because the cosine of a negative angle is the same as the cosine of the positive angle, we can just drop the negative in the angle. And with the sine of a negative angle is equal to negative sine of the positive angle, then this changes it from plus to minus. And so this gives us the two identities for sine of a sum and sine of a difference of angles. Sine of a plus b is the sine of the first angle times the cosine of the second, plus the cosine of the first times the sine of the second. Okay. Again, you'll notice that the sine of a sum is also a sum, and the sine of a difference is also a difference. We could then use the knowledge that tangent is sine over cosine, and so the tangent of a sum would be the sine of that sum over the cosine of that sum, and then we could simplify it. I'm not going to go through that proof. You can look at that proof online on YouTube or do a search, and it's also walked through somewhat in your text. But the tangent of a sum is equal to a quotient. In the numerator is the sum of the tangent of each of those angles, and in the denominator is 1 and either plus or minus the opposite operation of their product. So you can see the tangent of a sum is equal to the sum of the tangents of both angles, of each angle, and then 1 minus the opposite operation. Here we have plus, here we have minus of their product. And so the difference identity is similar, that the numerator has the same operation, a difference between each of the tangents of the angles, and then the denominator is the opposite operation, in this case a sum or addition of 1 plus their product. So let's try using these. Find the exact value of sine 75. Now, when we're asking you to find the exact value of a trig function, we're asking you to use known angles, which of course are all of our quadrantals, 0, 90, 180, and 270, and 360. in addition to all our reference angles, which remember are two reference triangles. We have 30, 60, 90 triangle, and then we have a 45, 45, 90. So we have 30, 45, and 60 are also known angles. So in this case, we're trying to figure out how do we use the sine identity to find the sine of 75. And of course, 75 is equal to 30 plus 45, two known angles. So we can use those known angles and then plug those values into the sine identity, the sine of the first times the cosine of the second, and then the same operation, so it's addition, times the cosine of the first times the sine of the second. Using our triangles, we can plug in the values for this, multiply these through, and we get the square root of 6 plus 2 all over 4. Okay? Which in quadrant 1 should indeed be positive, and we do see that there. Find the exact value of the tangent of 7 pi over 12. Of course, when I'm dealing with radians, I often try to think of these in terms of degrees, or I build my sample triangles and label them with radians as well. For example, 60 is pi over 30, 30 is pi over, 60 degrees is pi over 3 radians, 30 is pi over 6 radians, and 45 is pi over 4. In this case, I would then convert each of the denominators of those three angles, pi over 3, pi over 4, and pi over 6, into a common denominator of 12, and then see what I can do here. And in this case, pi over 3 plus pi over 4, or 60 and 45, create that same angle. Sometimes I'll also convert this back into degrees, figure out the sum or difference in degrees, and then convert it back to radians. So again, we just plug in. Remember that the numerator is the same operation, so it's a sum, and in the denominator it's the opposite, so it's a difference of their product. We can then plug in the values, and we get the square root of 3 plus 1 over 1 minus the square root of 3.1, which of course we then have to, that's the square root of 3, it shouldn't be the square root of 3.1. This is a typo here, please ignore that. And then multiplying the numerator and denominator by the conjugate of the denominator, we get 4 plus 2 times the square root of 3 over negative 2, and of course we can factor out the 2, okay? Or the negative 2, either way. All right, find the exact value of sine 40 cosine 160 minus cosine 40 sine 160. So as you're working with your homework, the key here is to get more and more familiar with the identities, and hopefully you notice that this is the sine of a difference of two angles, specifically sine of 40 minus 160. Okay? Again, I have another typo here. This should say 160, not 60. All right? So we get the sine of negative 120, which is also negative sine of 120 by the negative angle identity, and which gives us negative square root of 3 over 2. Typically when I'm at this point, I solve this in a different way, and that is I think about where this angle is. This is negative 120, so it's going in the clockwise direction, and it ends up in quadrant 3. Also, the fact that negative 120 has a reference angle of 60 degrees allows me to know that the sine of this angle is the square root of 3 over 2 by using our triangles for known angles. And then I know that sine in quadrant 3, which represents the y value, would be negative, so I know that this functional value is negative. So there's a couple of different ways that you can do this. So now we're going to look at how we can rewrite um, trig functions in terms of a function of theta, or the argument. So here we have cosine of 30 plus theta, tangent of 45 minus theta, and sine of 180 minus theta. Okay, so of course we're going to use the identities for each of these sums and differences, and then because all three of these angles are known angles, 30, 45, and 180, we can substitute the actual value in for those. So the cosine of 30 plus theta is equal to the difference between the cosine and sines of those, and the products of the cosines and sines of each of the individual angles. We can substitute in the value for cosine 30 and sine 30, and we have our solution here. This is just rewritten in another way, which is fine. We can do a similar thing with tangent 45 minus theta. We get the tangent of 45 minus tangent of theta over 1 plus tangent 45 tangent theta by just using the identity, and then substitute in the values for tangent of 45, and we get 1 minus tangent theta over 1 plus tangent theta. Finally, we do the same thing with sine, then substitute in the sine of 180 and the cosine of 180, and we get this into a much more simplified version, which is just the sine of theta. I'm not going to walk through these. To me, these are pretty straightforward. You're just using the identity, and then when you have a known angle trig function, you're substituting that value in. Okay. So let's look at a little bit more involved problem. So we're going to actually find the sum of angle A plus B. We're going to find the tangent of angle A plus B. And then we want to try to figure out what quadrant is the sum of those angles in. So we know that angle A, the sine of A, is 4 over 5. And we know that angle A is between pi over 2 and pi, which means that it's in quadrant 2. The cosine of B equals negative 5 over 13, and angle B is between pi and 3 pi over 2, which means it's in quadrant 3. Okay. We know that the identity for the sine of a sum involves the sine and cosine of each of those angles. And we know that the identity for tangent of a sum requires the tangent for both of those angles. So in order to solve this, we need to find, here's the values that we were given, the sine of A and the cosine of A. We need to find the other values, cosine A, tangent A, sine B, and tangent B. Now we can do this two ways. We can use identities such as sine squared plus cosine squared of the same angle equals 1 to find the other sine and cosine values. Or we could use the graphical method and use the SOHCAHTOA, drawing in, since we know that sine is equal to opposite over hypotenuse. We could draw these in on the graph in quadrant 2 and then figure out the other value, which would be the adjacent side for the cosine. Okay, so there's a couple ways to do this. We've done this in previous sections and chapters, etc. Because A is in quadrant 2, we know automatically that cosine of A is negative and tangent is also negative. Okay. So here we're going to use the identity of sine squared plus cosine squared equals 1. We substitute in the value for sine of A, and then we calculate the value of cosine. Since we know that the cosine is going to be negative, we use the negative square root of 9 over 25, which is negative 3/5. Because B is in quadrant 3, the sine of B is negative and the tangent of B is going to be positive. Again, we're going to use the Pythagorean identity. We plug in the value of cosine of B, and then we can figure out sine of B. We take the square root and we use the negative square root because we're in quadrant 3 and sine is negative. in quadrant 3. So we've already got two of our values, cosine of A and sine of B. If we wanted to find the tangent of A, now all we have to do is put the sine of A over the cosine of A. So 4/5 divided by -3. Okay. We can do this similarly with the tangent of B using the sine of B over the cosine of B. I'm not going to walk through all of these details. Okay. Remember, this is a division problem, so this is 4/5 divided by -3/5, which is the same thing as 4/5 times the reciprocal of the denominator, -5/3. And then we can see the 5's cancel out. Okay. So here's all the values that we have and that we'll need to find the sine of the sum and the tangent of the sum. Okay. So now all we're doing is plugging in values. We have the identity of sine A plus B. We plug in the values and do the math, and we get 16/65. We're going to do the same thing with the tangent of A plus B. We're going to first rewrite this using the identity. Then we're going to plug in the tangent of A and the tangent of B values and calculate. Okay. The last part of this problem was to try to figure out where A and B are. From parts A and B, we know that the sine of A plus B is greater than 0. We just saw that in the last slide. And the tangent is also greater than 0. So both the sine and the tangent are positive for the sum of those angles. So we know that the sine is positive in quadrants 1 and 2. And we know that tangent is positive when A and B, when the sine and cosine are the same polarity, the same sign, positive or negative, and that occurs in quadrant 1 and quadrant 3. So the only quadrant that these both are true in is quadrant 1. Sine is positive in 1 and 2, tangent is positive in 1 and 3. So since they're both positive, this has to occur in quadrant 1, and so that's where angle A plus B is. The last problem for the day is to verify an identity. And I think this one's going to be pretty straightforward, again, because we have known angles plus theta. So remember that when we're verifying an identity, or verifying that an equation is an identity, we only work with one side of the equation, and we work with the more complicated side, which of course here in this problem is on the left side. So what we're going to do is we're going to use the sine sum identity and convert this sine of a sum of two angles, and we're also going to use the cosine sum identity and convert this into the using the identity with these two different angles. And so we get that here. The sine is sine cosine. I don't like how they've written that. I like it when it's written the same way as the identity, which is sine cosine, cosine sine, but they wrote it sine cosine. It's not a big deal, but I think if you write it in the way of the identity, it helps strengthen your retention of that knowledge instead of writing it in multiple ways and potentially confusing yourself. Okay, and then of course we have the cosine of a sum is cosine cosine, the opposite operation in sine sine. Okay, so now we look at our known angles, pi over 6 for sine and cosine, pi over 3 for sine and cosine, and plug those values in. And then we look at what we have here. So notice we're adding a negative square root of 3 over 2 sine and a positive square root of 3 over 2 sine. So these are going to cancel out because we have the same number in front. This is just like sine theta minus sine theta since the multiplier is the same. So they're going to cancel out, and we're left with 1/2 cosine plus 1/2 cosine. Well, 2/2 of anything is 1 whole. And so we just get cosine theta, which is indeed the right side of the equation. So this is indeed an identity. Okay, that's the end of our lecture today. I've just put the three sum or difference identities here on one slide, hoping that would maybe help you in your recollection of these. Okay.